So first we'll define directly similar triangles. So they are similar, directly similar if they have like the same, they're similar and they have like the same orientation. So like if you are familiar with directed angles, it means that all their corresponding directed angles are equal as well. That's interconnections. So for example, here we have like ABC and say what A2, B2, C2. You can see that ABC and A2, B2, C2 are both clockwise in this thing, and but A1, B1, C1 is not directly similar to ABC or A2, B2, C2 because A1, B1, C1 is anti-clockwise. So the directed angle A1, B1, C1 is not equal to the directed angle ABC. So they are not similar. And also you have like the ratio condition that AB over A2, B2 is AC over A2, C2. And the LaTeX for this is like this plus and similar thing. So you can, this thing is the LaTeX. Oh, yeah, right. So this is the LaTeX for this. And if they are not directly similar, they are inversely similar. So for example, A1, B1, C1 is inversely similar to both of these triangles. And you use this minus and this thing, right? So for example, you can get an inversely similar triangle if you reflect this triangle in a line, because reflection does not preserve directed angle things. So if you now, right. So one thing is that if you say rotate or take a homothency, then directed angles are preserved. So for example, if you compose like take a rotations and homothencies, you send triangles to directly similar triangles. And so now we define a spiral similarity. Right. So spiral similarity at a point P is just like a homothency at P and followed by a rotation at P. So you can imagine something like, say there's a point P here. And if you say rotate ABC about point P and then just take a homothency, say if you rotate in this direction and take a homothency, you can send A to A2, B to B2, and C to C2. So the spiral similarity is just that, like it's, and the order does not matter, these two commute. So do you see why rotations and homothencies preserve directed angles? Hopefully that should be clear.
Yeah.
Right, thank you. And then there's this thing is that, see, there's a spiral similarity. If you take a spiral similarity sending ABC to something else, then that triangle must be directly similar. But the thing is, if you have any two directly similar triangles, then there must exist a spiral similarity taking ABC to that triangle. So for example, what it says is like, we must have some spiral similarity taking ABC to A2, B2, C2. Right. We'll show that in the next section. But one more thing. This is just equivalent to showing that there is a spiral similarity taking AC to A2, C2. Do you see why? If say a spiral similarity takes A to A2 and C to C2, why must it take B to B2?
Yeah, because of the similar triangles.
Yeah, because they preserve directed things. And this one, this is the thing. There is a unique point D such that for any triangle ABC and point C and F, so in our case A2 and C2, there is a unique point D such that ABC is spirally similar to A2, B2, C2. Now we'll construct this spiral similarity explicitly and show that this is unique. So, right. Right. for any two segments, say in our case, it's BC and EF, then there's either a spiral similarity or a translation taking BC to EF, right, B to E and C to F. So we can ignore the translation case because it's when BC is equal and parallel to EF. So now else we'll define the spiral similar center to be like we intersect EB and FC, let them intersect at A, and then you have let P be the intersection of ABC and AEF. Right. So do you see why there's a spiral similarity at P taking BC to EF? Okay. So, so what you really want to prove is that angle CPF is angle BPE because that is the rotation part, and angle CP by PF is BP by PE because that's the homotherapy part. So if there's that thing, then it takes B to E and C to F.
Angle CPF, did you say?
Yeah, CPF, yeah. CPF, all right. Go on, you're saying something?
Yeah, I was asking what angle did you say, angle CPF and which angle?
Your what is angle CPF? Oh, right. So we have to, if you prove that like CPF is BPE, then like that's because it rotates C to F and B to E. So if you prove that, and if you prove PB by PE is PC by PF, then that's the homotherapy part of the spiral similarity. So what are these two conditions equivalent to?
We have angle EPF equal to angle EAF, which is equal to angle BSC, which is equal to angle BPC, and then
right.
BPF is common. So we have angle EPB equal to FPC.
Yeah, that's correct. Yeah, so that's true. And you also want to prove the ratio part because, so like what is this equivalent to? I mean, the fact that there's a spiral similarity, yeah?
Like if we show the ratios are equal, then we have the...
Yeah, PB by PE is PC by PF.
Yeah.
So fine, we show that the rotation angles are equal, angle CPF and BPE. Right. And
Angle PBC will be equal to angle PEF.
right.
Yeah, so that will give the triangles are directly similar.
Yeah, exactly. So the triangles PBC and PEF are directly similar, and that gives us the ratio condition we want. PB by PE is PC by PF. Alternatively, we could have said that PEB is PFC. Like we could have proved that PBE is directly similar to PCF. So that's the second thing we have. That the spiral similarity, which takes center of the spiral similarity, which takes BC to EF, also takes BE to CF. Like it's the same thing, because taking BC to EF is equivalent to showing that triangles PBE and PCF are directly similar. But that is also equivalent to triangle PBC and PEF being directly similar. Does that make sense?
Yes.
Yeah.
So for example, here our rotation angle taking BC to EF was angle BPE. But now our rotation angle taking BE to CF is angle BPC equals angle EPF equals angle BAC. So, and also like this point P is unique. I'll show that later, but for now, let's assume that this point is unique. And so we can like apply this theorem to segments B and CF, because we applied this theorem to BC and EF to construct point P. And so applying this to B and CF should give the same point P. So these two circles, like if you intersect BC and EF at D, then BB and BCF should also pass through that point. I think you can also show this using angle chasing, that these four circles are concurrent at a point. But yeah, so P now we get is this spiral center sending BC to EF and BE to CF. And now here comes the rotation part. So now it's helpful to think of this rotation in terms of the angle between lines. So we'll focus on the spiral similarity taking BC to EF and show that it is unique. So if you rotate BC by an angle theta and it becomes some line EF, then the angle between BC and EF must be theta. Does that make sense? So suppose this angle, you rotate it by this angle and this angle. So you rotated line BC by this angle and then took a homothency, but homothency does not matter. But if you rotate BC by this angle, then the new line forms an angle equal to this with this line. I think one way to see is this, like if you say have BC, this is line BC and you drew a line parallel to BC. Now you rotate, say you're rotating about this point P and this is the line you're rotating. Now if you rotate by an angle theta, say like that, theta, then this also becomes something like this, theta. Because like rotation preserves parallel lines. Right. So what follows is that angle BDE should equal BPE. Like if there is a spiral similarity at P sending BC to EF, that is, it sends B to E and C to F, right? So angle BPE is the rotation angle, and it's also the angle between lines BC and EF. So BPDE is cyclic, so is BPCF. So that gives that P must be unique. So I'll give you like some time to think about this proof. And in general, it's useful to think about these as like angles between lines instead of angle chasing becomes much easier if you just like draw the lines and think of like these rotation arguments. And like you don't have to add some more new points to angle chase. You can just like draw these, intersect these lines, and yeah. So that ends what I wanted to say about theory. We'll cover some more later. But for now, any questions so far? Right. Right. So now, why is this? Wait. Yeah. So why is spiral similarity like a powerful technique? So one thing is that you can relate like unrelated points, like you can form angles between like floating points if you have a spiral similarity relation. So let's say you have a PBC directly similar to PEF for some triangles, and you have no way to relate like BCEF are like almost disjoint in the original diagram, but using spiral similarities, you get a new condition that PBE, PCF, these two are equal. So like B and E were earlier, they were completely unconnected, but you can relate them with each other. So I'm not being very clear with this. So one more thing. So one more thing is that if you have, say, a point P, and let's say you take some spiral similarity at P, taking segment P, and you evaluate one point. Let's see. Hmm. So you have, say you have this thing. All right. As a result, you get like, you can connect more points. Say you have the midpoint of AB and the midpoint of this thing. Then you have like this angle relation that the spiral similarity at P, which sends AB to A dash dash B dash dash, sends D to C, right? Because it should preserve the like segment AB. Now this gives us a relation like P angle 0 angle P A yeah, P A dash dash A, P C dash. So all of these are equal. And so like this thing, all these three triangles are similar. Should this right. So you get like a relation between C and D just because you have a spiral similarity sending AB to A dash dash B dash dash. So this thing is really powerful. And like you can form angles between midpoints of things, and like concyclic and say you have like concyclic conditions are not really good at handling midpoints of random lines, but you can do this. You can do these things with spiral similarities. So hopefully that convinced you that these are not completely useless. Right. So far we did this. Okay, now we'll go to our first problem. So can you see the problem?
Yeah.
Okay. So ABC is a pentagon such that these angles are equal. D is E, B, C, E, C, B, A, A, C. And we want to show that CE bisects BD. Right. Think of so any initial observations, like what is like
ABC and CDE are similar, no?
right? So ABC and CDE are similar. Are they directly similar?
But does it matter?
Are they directly similar or not?
Yeah, does it matter?
Yeah, it doesnn't matter because they're isosceles, so they are symmetric. But is ABC in that order similar to
Inverted.
CDE in that order?
Inversely similar, I guess.
What are you saying?
Oh, that should be directly right. If you just switch ABC, like yeah.
Right. Yeah, they are similar, but they are not
Yeah,
in fact
directly.
directly similar. If you take ABC and CDE in that order. But if you take ABC and EDC in that order, they are directly similar.
Yeah, so you can just switch the number. In the isosceles, it doesn't matter.
Yeah, but the thing is, there is no spiral similarity at C taking AB to D, because otherwise CBA would be directly similar to CDE.
Yeah, okay, got it.
Anyway, they are similar, so that's an observation. And think so. Right.
Does this have a projective solution also?
I don't think so. This is a grade 8 problem. It's last year's 8.7 Sharigan. No, but the spiral solution is pretty cool. Yeah, it looks because you have parallel lines and midpoints, right? So that's why you thought projective.
Yeah, and like angle bisector also.
Yeah.
EC is angle bisector, no?
Yeah, because you have this harmonic ratio, but no, the parallel lines and midpoints are not really this. It could have a solution. Yeah. Yeah, so AE parallel to CD is an important observation. So,
oh, right, yes.
right, I should. So I should. Yeah. AE. Okay. And you have this similar triangle. What is a good reference triangle with which you can consider this problem? So you have like DB bisects.
Reference for barycentric.
No, not bicentric, like just the point of view.
Oh, okay. I thought you were going to do barycentric bisecting.
I don't do bicentric. I'm not. So you have CDE and CAB. So these two are similar. CBA dash CBE dash. Okay, I think one way to phrase this is, suppose you had to construct such a pentagon. How would you start?
Okay, you can construct like CD, and then you can construct some X angle from DC at C. So
Yeah.
you'll get the line CE. You have angle CDE also, so you'll get the point E.
Right. Yeah. So you have constructed CDE.
Yes. Now you can construct a parallel from E to get A.
Yeah.
You get EA. You don't get A. Yeah.
Yeah. So you can vary A on the line through E parallel to.
Yeah, you can just take A anywhere, and then you can construct B because you have that.
Yeah. So that is how you do. You start with triangle CDE. You construct A and then you get B. So what I was saying is that if you consider this problem with respect to triangle CD, that makes it a lot easier. So what you're essentially doing is that you're varying A on this line. And you want to show that B moves such that BD is bisected by C. What does that mean? Okay, so yeah. So I'll repeat my question. So as you said, you start this problem by constructing triangle CDE. Then you draw the line through E parallel to CD. You vary A on this, and then from A you get to construct B. Now you're varying A on this line, and B moves such that, according to the problem, BD is bisected by C. What does that mean?
We should.
Reflection of D over.
Sorry?
It can't be the reflection though. So like you basically consider a reflection of D over every point of CE, and then
Right. So you take a homothency.
Homothency कहाँ से आया?
Like take a homothency at D with ratio 2.
Oh, right. Yes. So like the CA line goes to the locus of B.
Right. Sorry. This is homothency. Like 2. So B moves on this line as A moves on this line. Okay.
Yeah.
Now, what is the relation between A and B? How are they related? So you can think of it as there's a function from this line to this line. There's a function which maps this line to this line. What is that function?
Homothetic, no, you just said.
So as A moves on this line, B moves on this line according to the problem.
Yeah.
So there's what I was saying is that there's a function from here to here. What is that function?
So rotation,
Yeah, rotation and
dilation.
And homothetic.
yeah, exactly. So
Ah.
there's a rotation and homotheity because the factor CA by CB is fixed because CB is similar to a fixed triangle.
Oh, right.
So is this rotation factor fixed? So all we need to show is that this spiral similarity at C, which maps A to B, maps this line to this line. So we know about that this has ratio CA by CB, and it has angle equal to ACB. Right. So first things, can we prove that like AE gets mapped parallel to a line through this? Like what I mean is that what is the angle between line AE and the like image of AE under this spiral similarity? So like what I was saying is the spiral similarity at C maps this line to this line. Now, how can you determine, say we didn't know this, that this spiral similarity mapped this line to this line, then what would be the angle between this line and its image under this spiral similarity? Like you can think of like what I mentioned about rotating angles, rotating lines, and how they how you can angle chase using those things. Right. So does anyone have any ideas on how do you prove that the image of this line is this line under this spiral similarity? Okay.
We have to prove that the AE is mapped to the other line when we consider spiral similarity about C, right?
Yeah, so I'll do that. Yeah, we have to prove that this blue line is mapped to this red line under the spiral similarity. The red line is defined as like this line at a homothency at D with factor 2. And blue line is defined as the line through E parallel to CD. CD are fixed, we are only moving A, and B is also moving. So like, now, what is the angle between the blue line and the red line?
Will be equal to angle AEC.
Yeah, which is this angle, which is also this angle, which we want to show is the rotation angle. Okay, which is the rotation angle. So the rotation component of our spiral similarity is angle ACB, and the homothency part is CB by CA. Right. So one thing we know is that this blue line gets mapped parallel to a line parallel to blue line gets mapped to a line parallel to the red line. Now we want to show it is the red line. So for that, we need to add another spirally similar triangle. At say we want to make things spirally similar. So there's CBE. Okay, so we showed, for that we need to show that one point on this line under this spiral similarity at C gets mapped to one point on this red line. That would be enough, right?
Yeah.
So we want to show that the blue line gets mapped to the red line. Yeah?
Yeah.
So we know that by our rotation component that the blue line gets mapped parallel to a line passing through the red line. Parallel or coincident? So if we manage to show that one point on the blue line gets mapped to some point on the red line, then we are done. Does that make sense?
Yeah.
Okay, I'll repeat again. So from the beginning. So we start, this is how we think of the problem. We fix triangle CDE, which is isosceles. And the angle condition gives us that AE is parallel to CD. So we move A on the line through E parallel to CD, right? And then we can construct B such that CAB equals BCA equals this fixed angle. So we can construct B as a function of A. Now the problem also tells us that the locus DB is bisected by CE. Or alternatively, if you take a homothency at D with factor 2, it sends this line to this line. So B moves on a fixed line, which is as A moves on this line. And we have a function sending A to B, which is like this spiral similarity at C, sending rotation by this angle and with factor CB by CA. And if we prove that this indeed sends the red line to the blue line, then we are done. Because then it gives us that B lies on the, like, if you, the image of this line under homothency at 2 at D, so DB is bisected by CD, CE. So that concludes, and we have shown that blue line gets mapped line parallel to the red line. So if we show that any one point on the blue line gets mapped to a point on the red line, then we are done. Okay, do you see why the spiral similarity has to map line to a line? Yeah, because it preserves the shape. Okay, so why does it map this blue line to the red line? I should probably write. See. So
Can I see?
yeah, go ahead, please.
Yeah, so if we consider the map of E, it
Yeah,
will be point E dash such that the triangle E dash C will be similar to EDC. But as now this is this is like a reflection, and as the red line is just the reflection of D over the line CE, we get that E dash will lie on the red line.
right. So what is point E dash? Could you repeat that again?
It's the like consider spiral similarity about C. E is mapped to E dash.
Okay, right. So I think wait. E dash we can define as C. What happened? Okay, I think we've already defined E dash somewhere, so I'll call this E1. Right. So C E dash E, C E1E is similar to CBA, right? So what it gives is that C, this spiral similarity which maps A to B, maps E to E1. Now, since we know that CDE is similar to this fixed triangle, we get that CE1E is a parallelogram, right? Because like what E1CE should be equal to CED. So E1C parallel to CD. Now E is a point on the blue line, and E1 is a point on the E1 is a point on the red line, because if F is the midpoint of EC, and if you reflect D in F, you get E1. So the spiral similarity at C maps E to E1, and so it must map the blue line to the red line.
We define E1 to be the intersection of the red and blue lines, right?
Yeah, no, I defined it such that CE1ED is a parallelogram. Yeah, same thing. So, and by your definition, it's like CE1E is similar to CBA. So CE1E, this spiral similarity which maps A to B must map E to E1. So EA goes to E1B. Okay, right. So this problem was very instructive because you could like tell what the problem wanted you to do. Like most geometry problems, it's guess and check, but you can work backwards very easily with this one. And you can like thinking of spiral similarities as functions which map lines to lines instead of Like usually you think of the Mikhail point and then spiral similarities. So this is like really instructive. I'll give you a few moments to digest the solution. Does anyone have any questions or comments on alternative solutions? Okay, someone is suggesting bash. How do you bash this?
Somehow, like you
Yeah.
can see. I'll tell you the method. You can send CDE as reference.
Okay.
Then you will have equation of EA. You can just take A as any random point on EA.
Okay. Right. Yeah.
Right. And then since CD is similar to ABC, you can find B also because AB
As a
parallel to
function.
CE.
Yeah. And then you prove B is on this line.
Yep. Or like you can just prove like find BD cap CE, and then or basically you can just prove take midpoint of BD and prove that C midpoint and E are collinear because C and E are just like reference points, so they are nice.
Okay. Yeah. Yeah. I think someone did bash this in contest.
Yeah, like you can, of course.
Because something to do with medians and this. I think there is some median here.
Yeah, BE is the EC median in triangle ACE.
B is the EC median. Yeah, I think that's what he intended. Yeah.
Oh. Yeah, but my bash way is different, but yeah, that works too. Like it's not that messy. If you have determination, you can do it in like 30 minutes.
Right. Yeah, but thinking in terms of spiral similarities, it's like really nice.
Yeah, like of course, for starting motivation, you'll have to think about the structure only.
Yeah, yeah. This problem is so structured, exactly. So you can construct B as a function of A. So you think this function is actually a spiral sim. So this spiral sim maps the fixed line to fixed line, and then you have just like, okay, fine. Next problem. Okay, so this is the problem statement. Can we see it?
BPC is isosceles is that BP equal to PC?
Yeah, BBC is a right isosceles triangle. BPC, how did
Angle BPC is 90, right? Yeah.
Yeah, BPC is 90. NAB is 90. MA C is 90. So you have three right isosceles triangles, and you want to show that this is also right isosceles. This thing. Yeah. So okay. Okay. No. Yes, I think this is bashable more than the last problem, but no, we want to find a synthetic solution. Right. So what spiral similarities do you see in the diagram?
So BPC goes to NAB.
Sorry, again?
Oh, spiral similarity. So like B sends PC to NA.
Yeah, so we want to show that it's there's a spiral similarity at P sending BC to MN, right?
Oh, I said NA, but yeah. Like we have to show PC goes to NM, but like BPC PC goes to NA is also spiral similarity, right?
BC goes to
PC
goes
to NA.
NA.
Yep.
No, those are in fact inversely similar. Triangle BPC, because you can see that BPC is clockwise, BAN is, sorry.
Oh, right.
Yeah, BPC is clockwise, BAN is anti-clockwise.
PC goes to AN.
But there's also like there's also 90 degrees at this point.
Hmm.
Five participants. Okay, fine. So, right. So any other observations? Spiral similarities. One thing you see the condition is sorry, the problem asks you to prove that PBC is directly similar to PMN, right? So you want P to be the Mikkel point of BCMN, or I think some permutation. Oh, sorry, 7. So, right. Till how long can I continue this class?
How much time you need?
Now it's 7:42.
Yes. You can do till 8:30. Is that fine?
8:30. Like, okay, fine. I'll try to finish.
How much time you need more? Like till 8:45, it's fine.
Okay, till 8:45.
Is that fine?
Yeah, because anyway, if like we have only 4 people, not including me.
Yeah.
So if you're fine with it, then fine.
Yeah, I don't mind. Like if the other people who, if they are attending the next class, they are fine with till 9 also, I'm fine. I don't mind.
Okay, coming back to this problem.
Also, if
So,
you want, I can just create a poll till when the people want, and we can just do till then, 8:45 or 9.
okay.
I'll do that.
So coming back to this problem, we have like A and B directly similar to ACM. Right. So what does that give?
There's a spiral similarity. We can consider that.
Yeah, the spiral similarity which sends NB to CM. So A is the Mikkel point. So what does that suggest? Like what points should we add since A is the Mikkel point?
Mikkel point of?
Which sends NB to CM.
Yeah.
Because, okay, you can see A and B similar to ACM, and we have A and B ACM are both anti-clockwise. This, I think.
Maybe BM intersection CN.
Sorry?
BM intersection CN.
Right. So BM intersection CN. Let's call that K. Right? So what do we do with point K?
I guess angle K BKC will be 90.
right? So BKC is 90, right? Yeah.
So we get
Yeah, that's true. BKC is 90.
so we get as so we get then we get BKPC cyclic. Quadrilateral BKPC cyclic.
So, it says my internet connection is unstable. Can you hear me now?
Yeah,
Okay, fine. That's great.
yeah. So as PB is equals to PC, we get that PK is the external angle bisector of angle BKC.
Right. Yeah.
So now if we just need to prove that NMKP is cyclic.
MNKP is cyclic, right? But yeah, that would imply that P is the Mikael point. But do we not already have enough information to conclude that P is the Mikael point? That's what you want to prove, right? That P is the Mikael point of which sends Mn to BC. Okay, so we want to prove PMN is fairly similar to PBC, which is equivalent to what? Okay, also, how did you get that BKC is 90, Malay?
Just like K is the, we get rotation about K. So
Right, yes. So A is the Mikael point, so A is also the intersection of these two circles. Okay, one thing we also have is that since CN intersection BM lies on this circle, so we have, because since PCBK is cyclic, angle PCN is PCK equals PBK equals PBN. So we have angle, sorry, we have okay, right. So we have PCN is equal to PBM. Now, what else do we need to show that PMN is isosceles and right triangle? Oh, we also have PC equals PB.
Or we have angle PNC is same as PNK, which is PMK, which is same as PMB.
Right, but for that we need NK-PM cyclic, right?
Oh.
Yeah, that would imply our problem, but yeah. So what are we aiming for?
We just need CN is BM, which can be proved by CN is common to MA.
Sorry, you were saying that CN is?
We need CN is BM.
Oh, you were saying PCN congruent to PBM.
No, CN is BM. ABM is congruent to ACN.
So were you saying that CN is equal to BM? Your voice is like slightly breaking, so could you type that in chat? ABM is equal to A and C. Right. ABM is equal to A and C because right, BM is equal to CN. Yeah, exactly. That finishes. So we have BM is equal to CN, PB equals PC, and PCN is equal to PBM. So that gives triangle PBM is directly similar to triangle PCN, which gives PCB directly similar to PNN. Does that make sense? Okay. So Cn equals Bn. Okay. Bd equals Bc. Right. So we have these two triangles are similar. So spiral similarities come in pairs. So if P takes Bn to Cn, it also takes Bc to Mn. Right? So that finishes. So what did we use in this problem? So we started with A and B is spirally similar to ACN. So by using spiral similarities come in pairs, we got A and C, which is, okay, change. Oops. Right. So we started with A and B is spirally similar to ACM. Then by applying spiral similarities come in pairs, we got A and C spiral similar to ABM. And in fact, they must be congruent because AN is equal to AC and AB is equal to AM. So that gives BAM equals CN. And also the Mikhail condition gives us that their intersection K lies on the circle with diameter BC, because like BKC is BPC, like BKC equals BKN is equal to BAN. So we just applied this thing multiple times and we got what we wanted. There's also a slick solution using just rotations, which I'll like give you a link to after the class. Just the one-liner. Right. Okay, now we'll move on. Fine. I want to cover something new. So this is the coaxiality lemma, which says that if you have, say, two circles, let's say this and this, and suppose they intersect at X and Y, right? Let's see. Suppose we have two circles which intersect at X and Y. Do any of you know the statement of the forgotten coaxiality lemma? Okay, so that's a no. Fine. So you have 2 points P and Q. P and Q. And we claim that XPQ is coaxial with these two circles. Sorry. XPQ. Let's move Q a bit. Okay. So XPQ is coaxial with these two circles if and only if XPQ coaxial with these circles if and only if UX C1 B missing something. Okay. Okay. So XPQ is coaxial with, say, this is C1 and this is C2. If and only if the power of P with respect to C1 over the power of P with respect to C2 is equal to the power of Q with respect to C1 over the power of Q with respect to C2. Right. So how is this related to spiral similarities? How do you think this should be related to spiral similarities? Did you get the question?
Yeah.
So have you seen this before? Right. Okay. Fine. So how is this related to spiral similarities?
We can let line XP intersect C1 at say P1.
Right.
P okay P1
Yes.
and C2 at P2.
Yes.
And now similarly for XQ we get Q1, Q2.
Yes. Yes.
Now we have to prove that there is a spiral similarity centered at Y that maps PQ to P1, Q1.
Okay. Yeah. Okay, that's equivalent to this.
Yeah.
So because if there were a spiral similarity sending P1, P2, Q1, Q, then by our Mikhail point construction, we have XPQ lies on this, right? Now, how do we use this? What is this condition equivalent to? Power of C1 over P over power of C2 over P equals power of C1 over Q.
Oh, PP1 over PP2 is QQ1 over QQ2.
Yeah, PP1 over PP2 is QP1 over QP2. Okay. Yes. So now there's a spiral similarity sending P to Q, P1 to Q1. But okay, now we already have a spiral similarity sending P1, P2 to Q1, Q2 by definition.
Yeah.
Now, where does this send point P? So rotations and homotopes preserve the shapes of lines, right? So like if P has this ratio with P1 and P2, then if it gets to map to some new point P dash, then that also has this relation, right? So the spiral similarity which maps P1, P2 to Q1, Q2 maps P to Q. So P, we have like X, Y, P, P1 is spirally similar to Y, Q, Q1. So Y is also the Mikael point of P, P1, Q, Q1. And that gives you the coaxial condition.
Yeah.
So if you vary P, say, okay, ideally we should have fixed P1 and Q1. But say if you fix P1, Q1, P2, Q2, and you move P and Q such that this holds, right, someone did a poll, you can answer that.
Yeah, for like class and I just put it.
Can I vote? No.
Nah, you are host.
Why is there a right now option?
For the sake of joke.
Okay, fine. Okay, it's already 8-8. So let's imagine that P1, P2, Q1,
People
Q2 are
answered the
fixed.
poll also. You can see.
Okay.
8:45 suits, Ananda.
Okay, fine. We'll try to end at 8:45.
All right.
Let's imagine that P1, P2, Q1, Q2 are fixed and P and Q move such that this holds. Then this XPQ always passes through Y. So you can imagine that P and Q are moving with constant velocity. Constant velocity ratio is always preserved. And so XPQ is always passes through the fixed point Y. Now, say, for example, so if you have, say, a triangle, I'll delete everything again. You have a triangle, say, A, B, C, right? And say you have points D and E moving on AB's lines A, B, and AC with constant velocity. Then ADE always passes through a fixed point. This circle always passes through a fixed point. This is what the coaxiality lemma is saying. So if you like move D and E with constant velocity. Now, if you remember from Malay's class, we had this problem. The problem was point D, I think, and then you drew parallel lines from here to here and from here to here. E and F. And you were asked to show that AEF always parallel, always passes through a fixed point. So the proof you can do this. So in that class, we actually characterize that fixed point. But you can also do this with just the coaxiality lemma. See, because E is moving with constant velocity. If you move D with constant velocity, so is F moving with constant velocity. And so like if you fix, say, some two positions of D, say call this D dash, and draw the parallel lines. D dash, F dash. So, right. So you fix 2 points, E dash and F dash, sorry, D dash and D, Now for any point, say here, say G, and then again you draw parallel lines. Okay, we call this, sorry, we'll call this D1. We'll call this E1. And we'll call this F1. Right. So do you see why E1 over E1 E dash is equal to F dash F1 over F1 F dash F1 F?
Yeah.
Yeah. So because if you say fix D and you are moving this, then this is equal to D dash D1 over D1 D. And so you have this, like, points are moving with constant velocity, and AEF passes through a fixed point, which is the Mikael point carrying, in this case, it was the Mikael point carrying BA to AC. So it might be different for like different velocities. So in any case, if you have like a problem, a setup which involves points moving on lines AB and AC, and this circle passes through a fixed point, then the idea is always like that there is a spiral similarity involved. I think there's one more problem which involving this thing where the fixed point is the Humpty point instead of the Dumpty point. I don't remember which one. I think it was some Elmo problem. Right. Okay. So this is one thing I wanted to discuss. So this is like really cool. If you have points moving with constant velocity, this circle is always passes through a fixed point. And then the next thing I want to discuss is the gliding principle.
Yeah, this was nice.
Yeah. So gliding principle says that, yeah, this is even cooler. If you have, say, fixed spirally similar triangles ABC, let's create another, let's have a point P and rotate, say by 45. 45 is. Yeah. So we have, say, spirally similar triangles ABC and A dash B dash C dash. The thing is, if you take, say, this segment, say A dash B B dash C C dash, and let's say you take their midpoints, midpoint, midpoint. Then the gliding principle says that DEF is in fact similar to both ABC and A dash B dash C dash. So let's move. Okay. Green. Yeah. Right. So all these three triangles are similar. You took the midpoints of these segments, so A dash, B dash, C dash. In fact, you could have taken, like, divided them in any ratio. Say you could have divided them in 1:2 ratio or any ratio you wanted. But in our case, let's say you take their midpoints. Now, do you see how to prove this? What should the proof involve? Like, so it's like quite similar to the proof of the causality lemma. So what should it involve? I think you can also bash this. If you take like complex numbers, it shouldn't be too bad. One case where So okay, so we are down to 4 people. So 4 is 0. Okay, so the idea is again like the spiral similarities come in pairs. So if there's a spiral similarity taking AB to A dash B dash, there is a spiral similarity taking A dash to B dash. This has been like used in most problems in this lecture. So that's the main idea.
And spiral similarity will take D to E.
Yeah, exactly. So PDE is similar to PAB. So how do we prove that, say, angle EDF is equal to angle BAC? This spiral similarity, wait. Let's see. Okay, so we have PDE, spiral is similar to PAB and PA dash B dash. And say we want to prove that FDE is equal to CAB. How do we finish? Yeah, So as Pranav said, sorry, not Pranav, Kanav. PDF is spirally similar to P-AC. So let's say PDF is spirally similar to P-AC. So adding these two, we get that PDF plus, sorry, PD minus PDF is PAB minus PAC, which is like BAC. Similarly, you have the other things. So EDF is spirally similar to this, this, and this. So one cool application is Napoleon's theorem. So if you have, say, a triangle A, B, C, and B, C, 3. Sorry. Three. So let's say centers. So O1, O2, O3 is in fact an equilateral triangle. So BBC, FAC, AEB are all equilateral triangles. So O1, O2, O3 are their centers, and show that this is in fact an equilateral triangle. Is this in EGMO chapter 6? I think you complex partials.
Yeah.
Yeah. Okay, so you can also do this using just spiral similarities, the gliding principle. So any ideas? Let's work backwards, right? So let's just take two equilateral triangles, say these two, and we want some linear combination of their segments, which is nice, which gives us like nice points. So can you think of something, say on segments EO3, AO2, and BO1? Okay, it's almost 8:30. Suppose. Okay, so the thing is, we have these midpoints, say G, H, and I. Now O1I over O1B, O2G over O2A, these are all like 1:3 ratios because O2 is the centroid. So it's equivalent to proving that, have I got this right? Sorry. What was it? Yeah. Yeah, it should be this. Sorry. So if you take these 3 points, they all are like divide this segment in a fixed ratio, 1:3. And so if we prove that HGI is equilateral, we are done. Where H, G, and I are the midpoints of CF, CD, and AB. Now, how do we finish from here? Wait, is this true? Yeah, this is true. So H is the midpoint of AB, I is the midpoint of FC, and G is the midpoint of CD. How should we finish from here? Uh-huh. Exactly. ACE and BDC. So ACE and BDC. So you have H is the midpoint of AB, G is the midpoint of CD, and I is the midpoint of CF. So you're averaging the triangles ACF and BDC. Is that clear?
Can you please repeat that?
Okay, so we are just applying the gliding principle twice. So what we were working backwards actually. So first we showed that this is equivalent to proving that GHI is equilateral, because we applied the gliding principle to triangle EAB and triangle O1, O3, O2. So EO3, we have point H on line EO3, I on line AO2, and G on line BO1. So, and you can see that these ratios are fixed. GO1 over GB is 1/3, HO3 over HE is 1/3, IO2 over IA is 1/3. So this is in fact like a linear combination of, what do you say? Not linear combination, I think weighted average is the better word. So O1, O2, O3 is a weighted average of orange triangle and this green triangle. So since both of these are equilateral, this will be equilateral. We want to show that this is equilateral. And now so since these H, I, and G are the midpoints of AB, CF, and CD, so we again take the weighted average of BBC and AFC. So H is the midpoint of this, then this, and then this. Is that clear? So AGI is equilateral, and then it follows that blue triangle is equilateral.
Yeah, okay. Thanks.
Okay. Now we come to the final problem. I think this will take a while. It's 8:30. All right. So this is really cool. Don't think I have to straighten this. Hmm. Ah. Oh, I think should be easier. How do I copy the text? Okay. AB and CD. That's the reason. Okay, I'll stop share for. Okay, stop share. Sorry. Okay, meanwhile, you can check out the statement of ISL 2000 G6. I'm having trouble pasting it here. So this is the next problem. Okay, I finally have it. Okay, can you see my screen now?
Yes.
Right. So this is the problem. Open CD. Rename. Show how many. Oops, I'm revealing scopes. Ah, this is great. Okay, fine, finally. So this statement is really cool. We have AYB is to ADX. So we have that angles XAD equals angles BCX. Sorry, what? Yeah, ADX is BCX and DAX is CBX. These are not directed actually. So the AOPS statement uses directed angles, but these are angles are not direct. So actually, XAD and XBC are in fact inversely similar, not even directly similar. And it says that if XAB and the statement just says that if XAD and XBC are inversely similar, then angles, you can determine angles XD and XAD. So it says that basically this point X is unique if the problem statement is true. So you know that there's a unique point X such that XAD is directly similar to XBC. So this says that if like, except for some edge cases, the point X such that XAD is inversely similar to XBC is also unique. Now the first thing we want to do here is like, since we have inversely similar triangles, we can't deal with this very nicely. So how do we convert inversely similar triangles to directly similar triangles?
Maybe reflect.
Yeah, reflect, exactly. So what do we reflect?
Let's reflect one triangle about some line through. Wait, what shall we reflect?
Okay. Also, keep in mind this AYB equals to ADX. So what do you want? For now, let's restrict ourselves to like, how would we go about constructing point X?
Oh, can you
Yes, reflection is a good idea because reflecting will give you directly similar triangles. Yeah. No, I didn't say anything, Pranav.
Okay.
Okay. Yeah, reflection is a good idea. What do we reflect? To really get some.
Maybe about perpendicular bisector of AB and some other perpendicular bisector of CD.
Some so do you want me to add perpendicular bisectors of AB and CD?
Yeah.
Okay. Yes. And then so do you want me to reflect this about X about perpendicular bisector of AB?
Yeah.
Okay, I see. So A goes to B. Let's reflect D. Okay, just X you want. Or do you also want
No, the whole triangle ADX.
D in here? Right. So we have BX D1 is similar to BXC. Yes?
Yes.
Okay. And that is equal to, what do you want to prove? We want to prove that XDA is half of BYA. So XDA is BD1X is half of this. Okay. So okay, so we only have 5 minutes left. Unless both of you are okay with some more time. Do you plan to attend the next class?
I'm fine till 9.
Yeah, okay, maybe Kanav is okay, fine. Then maybe I can leave this problem as homework, but this you should really try. This is brilliant. So Not easy, but yeah, you should really do this. This is a good idea. So one thing is that this BYA equals to BDX reminds you of the circumcenter thing, because the angle subtended at the circumcenter is twice angle subtended there. Yeah, actually this isn't my solution path, but I think this is still promising. So you reflect X in this bisector and this bisector. Oh, but this is okay. So this is a cyclic quadrilateral. Okay, since we have like say 10 minutes left, should I walk you through my solution path?
It's fine.
Yeah, I think that's better.
Yes.
Yeah. So what I wanted to do was I reflect them in AD and BC. So you have reflection. X in AD, X in BC. Now, okay. AX dash D is similar to BXC. So this spiral similarity which takes AD to BC takes X dash to X. Similarly for this thing. So let's say, how do you construct? I'll remove the statement now. Is that fine?
Yes.
Okay, yeah. So we can construct the Mikhail of AD and BC. Say, let's call this. Let's call this G. Right. So G takes actually, how do I bring this part back? Yeah, this is better. Sorry, G. Let's hide these two. Right. So G is the Mikhail which sends AB to CD and AD to BC. Now G sends X dash to X. Can you see why?
Yeah.
Because G sends ADX to BCX. Similarly, G sends X1 dash to X. In fact, G is the dumpty of X dash X X1 dash, because it sends X dash X to X X1 dash. So G is the dumpty. Right. And now we apply the gliding principle. So we have on triangles AX dash D and BXC. So actually, we see that this reflection condition is that so the midpoint of AC is like you want to add that because you are reflecting about this point. So you want to add these. Why is this point not being added? Okay, let's say M1 equals and 2 equals X by 2. Yeah. So, okay. Also, what we wanted to show now becomes very natural. X dash dx is AYB. This is what our problem reduces to. Okay. So now we add these two things, N1 and N2, and we like basically take the average of triangle BXC and AX dash T. So we have the midpoints. Where did I have them? So by the gliding principle, let's move orange. M1 and M2 and M1, N2, M2 are in fact inversely similar. So what does that mean?
Can you please repeat?
Okay. So first we reflected, you got this part that AX dash B is similar to this triangle BXC.
Yeah, no, can you please repeat what two are for M1, M2?
M1 is the midpoint of AB and
Okay.
M2 is the midpoint of CD. Basically, we are averaging these two triangles by taking their midpoints, the gliding principle. So the midpoint of BA is M1, the midpoint of X dash is N1, and the midpoint of CD is M2. So orange triangle similar to pink, 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 pink. Similarly, this orange, all of these triangles are similar. So what this means is that N1 and N2 are reflections of each other in M1, M2, because these two triangles are similar.
Yeah.
Now, with this, we can construct X because, say, this is how we construct X. We take line AB. In fact, this is how I constructed X in my diagram. We take line AB, we reflect it in line M1, M2. Where is that thing? Yeah. Yeah, so this, okay, I'll do it again. I'll reflect this in this. So if I reflect AD in M1, M2 and intersect, suppose that intersects at a point N2, then we reflect N2 back in M1, M2 to get N1, then we know that M1 and M2 is similar to M1, N2, M2, right? So you know why, do you get why points N1 and N2 are unique?
Wait, how do we define N1, N2?
Okay, so let's just, yeah, sorry. Let's say we don't know what, I'm telling you how to construct X. So initially I defined, of course, as the midpoint of X dash and X1 dash. But suppose we want to construct X given ABCD. How do we do that? That was what I was telling you. Sorry for confusing. So let's erase everything almost. Let's erase X. Where is X? Okay. Suppose we don't know anything about X. We want to construct X. So we know that if the perpendicular from X to AD and BC are N1 and N2, then N1 and N2 are reflections across M1 and M2. Is that clear?
Yeah.
So basically, if we reflect AD in M1, M2, then, and that becomes, say, this line, say this red line, then that intersects BC at N2. And if we reflect N2 back in M1, M2, then these 2 points are reflections across each other. And this one lies on AD, this one lies on BC.
Yeah.
So we can then take the perpendiculars from N1 to AD and N2 to BC, and they can intersect at X. X, where is X? Where is it? Okay, X. So this is how we construct X. So now let's get back here to our problem. So what we want to show is that angle N1, M2, N2, which is twice of ADY, is AYB. So how do we go about proving this? There's more spiral similarities. Actually, I think I'll leave this as homework to you. It's already 8:52. So right, this is where we end our class. You can also try continuing that approach you were talking about, reflecting X in the perpendicular bisector of AB.
Oh, by gliding on GAD and GBC, we are done, right?
Sorry?
By gliding principle on GAD and GBC.
GAD and GBC. Oh yeah, so that gives that GM1, M2 is similar to GAD and GBC, right? That is correct. Let's say black.
Right again, I was just something wrong. Forget it.
Right. I think, yeah, that. So we know that we want to show that, say, AYB is spirally similar to N1, M2, N2. That would finish. Or see, thing is, we want to reduce it to lines we are comfortable with. So we are somewhat comfortable with lines M1, M2, because in terms of ABCD, but not so much with N1 and N2 because they are defined somewhat randomly. So if we show that M1, M2, if we show that this problem is equal to a spiral similarity sending M1, M2 to some other line, then we are done. We are done, like we can finish it easily. So we want to ignore points N1 and N2 and find the spiral similarity which sends M1 and 2 to some other. So I'll leave this as homework. Thanks for attending. So you can stop recording now. Pranav, is he there? Pranav, are you there? You can stop record. Oh, okay, anyway. So what I wanted to say was, are like other classes also low as this?
Yeah.
Or is this the only class with 2 people attending?
It's usual.
This is